Okay, good morning, guys. Today we are going to speak about fluid particle reactions. So we are speaking of a heterogeneous system and not a homogeneous system, and that's what you must keep in mind. Now, before we continue, please don't forget to subscribe to the channel. Now, as you see here, we are speaking about heterogeneous non-catalytic solid fluid reaction system. I specify on non-catalytic because further on we will work with solid catalyzed reaction which will change everything. Now, what are the possible reaction schemes that can occur? So we'll assume that A will be in the external phase that will diffuse to react with the in the particle, which is in the solid phase for sure. Usually it will be a gas-solid reactions, and the same will apply for a liquid-solid reactions, but usually the work will be with a gas-solid reaction. So if we have an A, which is fluid, reacting with B, the stoichiometric coefficient, times B in the solid of the particles, we might have a fluid product, a solid product, or a fluid and a solid product. Now, many possible ways can happen. In reality, two ways can happen when a reactions occur. First of all, and the first way that must occur or may occur is that the particle during reactions will form a non-flaking ash around it, an ash layer that is non-flaking, which means that it won't go away, and thus we end with a completely reactant particle of unchanging size. You see, first the initial particle and the completely reacted particle has the same size. However, we might have another way, which is that the particle can form a flaking ash. When we say a flaking ash, it's an ash that can goes away, and thus the particle will shrink in size during the reactions. So this is our initial particles, and due to the flaking ash that the particle was losing it, we ended up with a very small particle at the end. Mainly it will disappear, and this the case when, for example, when you take the reaction of the combustion of coals, for example. Now, the kinetic models that can be used for particles of not changing in size. So we go back, not changing in size. We are saying that we have an ash layer that forms. In the other case, no ash layer is formed. So here we are speaking about ash layer that forms. The first model that we can deal with is the progressive conversion model. In this progressive conversion model, the gas reactant A, or in the fluid if it's in the liquid phase, will diffuse and react in the particle progressively and continuously at all the locations. So the reaction is taking place at different locations progressively, and the concentration thus in the reactant particle will decrease with time as the reaction proceeds. Now, the other model that we can deal with is the shrinking core model, and this is the most important model for particles not changing in size because mainly it's used in practice. And thus, since it's applicable for most of our applications, we will be solving the equation based on this model. In this shrinking core model, many steps can occur, but let's take a general look on it. First, the reaction will occur at the outer skin of the particle, and then the reaction zones moves into the solids. As you can see, it can move into the solids. So it was here. The reaction takes place at this side, for example. Then it drops to here, leaving behind a completely reactant part of the particle, and this part, the white one, is the unreacted core. Now, what are the steps that might occur in the shrinking core model if we assume that we have a spherical particle? We can have diffusion of the gaseous reactant through the film surrounding the particle of the surface. So it comes to assume, or maybe I can show you on the other slide, yeah. So we assume that we have A in the reactant, we have A in the bulk fluid. It diffuses until it reaches the stagnant film, that the gas film that will be surrounding the particle. Then it will diffuse into this stagnant film until it reaches the particle surface, and then it will react with it initially, but then we will have an ash that will form. So it will diffuse into the ash and react on the part of the unreacted core. So you can see that many steps can occur. And during the steps, we might have that the diffusion through this film will be a limiting step. The diffusion through the ash layer might be a limiting step, or the surface reaction might be a limiting step. Today we will be going to look about the gas diffusion as the limiting step, or we call gas diffusion controls. Now, since the reactions occur at the surface of the particle, it's better to work with the rate based on the surface, the exterior surface of the particle. So we say that from the rate minus 1 over the exterior surface, as the reaction will be taking place at the exterior part of the surface, times the variation in the number of moles of B with respect to time. Here we are just substituting for S exterior, which is 4 pi r squared dmB over dt, because it's a sphere and the area for the sphere will be just 4 pi r squared. Now from the stoichiometry, if you go back, we said that we have A plus B times B will give the product. So from stoichiometry, it's B times dNA, it's nothing, just some basics, over 4 pi r squared dt. And then this variation, as we are assuming that it's gas diffusion controls, it's equal to the diffusion that occurred in the gas film. And since diffusion controls, I must tell you that the profile will look like that. No concentration gradient in other steps like the diffusion in the ash layer or in the surface reaction. The concentration gradient will be just in the gas film. So this variation in the number of moles with respect to dt and per surface must be is equal to B from the stoichiometry times kg, where kg is the mass transfer coefficient in the gas phase, times the difference in the concentration gradient, which is CAG minus CAS. Now, when we speak about gas diffusion controls, CAS will be 0, so we have a high concentration gradient, and that's why it controls. And this will reduce to B kg times CAG, which will be equal to constant at the end, because the concentration in the bulk fluid here will always be constant. It's not varying. So all this equation, equating these two parts in fact, will be always equal to constant. Now, what we need to do is that to express the number of moles of B in a way that allows us to solve the equations. Now, for the number of moles of B, it can be written as the rho B times B. And here you must note this rho B, the density. You must not get lost or with the density of the density that you know, which is kilogram per meter cube. In fact, this is the molar density. It's in moles per meter cube of solid. And thus, moles per meter cube of solid times meter cube of solid from the volume, we end up with moles. So the units are coherent with each other. Then minus dNB equal minus B times dNA from the stoichiometry. And substituting for from here, if we do the derivation of dNB, it's equal to rho B times dV, as rho B, the molar density, is constant. So we only differentiate the volume. So we have minus rho B times d, the derivative of 4 over 3 pi RC3. Why? Because the volume of the unreacted core is where we will find B. Because the other way, if we in the ash layer, no more B, because the reaction has proceeded and we have only the product. So that's why we deal with RC and 4 over 3 pi RC3, because as we said before, we're assuming a spherical particle. Now differentiating 4 over 3 pi is for sure constant, goes out of the derivative, and we end up that we have minus 4 pi rho B RC squared times DRC. Now if we place this in the previous equation that we had, and we rearrange the equation so that we have minus rho B over R squared, as R squared and rho B are constant, we can put them out of the integral. RC squared DRC equal to B times KG CAG integral from 0 t dt. And here we integrate from R to RC. You will say, oh, why you are not integrating from the small radius to the big radius, like from RC to R? You can see that there is a negative sign here, and it's logical because with the reactions zone, as I said, it moves toward the center, so it's moving in the negative direction if you want. Now integrating these two, just basic integration, nothing. Integral for RC squared, the RC is RC power 3 over 3, and substitute from R to RC, and rearranging to get T, we get this value. Now this T is the time needed for conversion of a radius for a particle of radius R, for example. And now what is tau? Tau is the time needed for the complete conversion of a particle of radius R. How we get it? So what is a completely convergent particle? It's when no more we have an unreacted core, so we say that RC is equal to 0. So this term we neglect, we end up with a one term in the brackets, and thus we end up that tau is equal to only this term, which is rho b times r over 3 times b times kg times ch. Now some analysis can be made on this expression. We see that the time needed for the complete conversion when gas diffusion controls our steps is dependent on r power 1, so on just r. So the bigger the radius, the higher the time needed for the complete conversion to reach, as well as the most important term is here, the kg. So the higher the mass transfer coefficient in the gas phase, the lower the time needed for the complete conversion, which seems logical for sure. The more I can supply my reaction surface with the reactant, the more fastly I can do that, the more fastly I can do my reaction and reach the complete conversion. Now XB here, let's say what's XB first. XB is the conversion of B. So 1 minus XB for sure, it's the amount that is not, the fraction that is not converted yet, which can be written as the volume of the unreacted core to the total volume of the particle, which is logical. The volume of the unreacted core, it's the part that didn't react yet, and the total volume of the particle, and thus 4 over 3 pi RC cube, which is the only part that didn't react, over the total volume, so it's R power 3. We see that this simplifies to RC over R power 3. Now if we do just, we had before the expression for T over T, and we had the expression for tau. Dividing these the two by each other, T by tau, we will kept with the terms in the bracket, which is 1 minus RC over R power 3, and we set 1 minus XP is equal to RC over R power 3. So XP, if we take XP to the other side, we have that XP equal to 1 minus RC over R power 3. So thank you for your attention, guys. I hope you liked the video and you got benefited from it. Thank you.